picture this, right? You are handed a massive hard drive.
Oh, boy.
Yeah. And on this drive is every heated forum argument, every dense Wikipedia page, every bot-generated spam email, and basically every repository of open source code ever written.
So an entirely unstructured, chaotic data swamp.
Exactly. Just a complete mess. And your boss walks in and says, hey, I need you to build a system that reads all of this, understands the complex logic behind it, and can answer any arbitrary question about it.
Right. Good luck with that.
And here's the kicker. You are not allowed to write a single if-else statement or hard code any business logic.
Yeah, I mean, any sane developer would just walk away.
Oh, 100%. You tell them to find another engineer.
Because approaching that level of unstructured chaos with traditional programming paradigms is, well, it's mathematically impossible.
Right.
You can't manually map out rules or, edge cases and state machines for the sum total of human digital output. The state space is simply too large.
Welcome to the Deep Dive, everyone. Tonight, we are opening up a stack of notes focusing on the fundamental engine of modern artificial intelligence, which is pre-training.
Yes, the big one.
The really big one. Our mission today is to tear down that mystical sci-fi aura surrounding how these massive models learn human language directly from the internet.
Because it's really not magic.
Not at all. We want to translate the theory into the brutal, actionable engineering realities for you, the software engineer, tuning in right now.
Yeah, peeling back the curtain reveals that, at its core, building these systems is just the ultimate exercise in systems engineering.
Right.
It's distributed compute architecture and data processing. We are dealing with raw optimization on an unprecedented scale.
So keeping that chaotic data swamp in mind, we have to look at how we actually compile that noise into executable logic.
Right, the core loop.
Yeah. Before we even touch on what an AI model outputs to a user, we have to understand how it learns without human handholding. And looking at the architecture in our sources, it all hinges on something that sounds, honestly, almost too trivial to be true.
Next token prediction.
Right, next token prediction.
It is a deceptively simple mechanism, but it is the engine of scale here.
Okay, unpack that a bit.
So pre-training basically relies on feeding the model a sequence of tokens. And a token is roughly a chunk of a word or maybe a snippet of code.
Gotcha.
And you just ask it to predict the very next token. And you do this across trillions of tokens, just over and over and over again.
Okay, I have a pushback on the framing there, though, because, my phone's keyboard uses next token prediction to suggest the next word in a text message.
Yeah.
And it operates on a relatively simple statistical model. And I can assure you, my phone does not know how to write a highly optimized Python script.
No, it definitely does not.
Or, debug a Kubernetes cluster. So how does scaling up a game of guess the autocomplete suddenly cross the threshold into reasoning and complex logic?
Well, the difference lies in the complexity of the sequences the system is forced to resolve.
Yeah.
And, the sheer depth of its architecture.
Okay.
Like if I give you the sequence, the quick brown fox jumps over the lazy...
dog.
Right. Simple statistical parroting tells you the next word is dog. You don't need logic for that.
Fair enough.
But consider a scenario where the input sequence is half of a complex, completely undocumented asynchronous function in Rust.
Oh, wow. Yeah, okay. To accurately predict the next line of that Rust code, I can't just rely on statistics.
Exactly.
I would actually have to, trace the variables, understand the memory management constraints, and basically infer the entire logic of what the function is trying to do.
Which is the fundamental leap in understanding pre-training. To get the prediction right consistently across all domains of human text, statistical parroting completely breaks down.
It just can't keep up.
Right. The model is forced by the training process to build an internal mathematical representation of the rules that govern the text.
Okay, so how does it actually build that?
Well, when it guesses a token incorrectly, a mathematical error signal is calculated. And that signal propagates backward through the system.
Backpropagation.
Yes, backpropagation. It makes these micro adjustments to billions of artificial connections.
Let me make sure I'm getting this. So when the model guesses, say, cat, and the actual next word in the training data was dog,
Yeah.
that error signal slightly tweaks those billions of connections, right?
Right.
So that the next time it sees a similar context, it's a fraction of a percent more likely to guess dog.
That is exactly it. And when you multiply those microscopic adjustments by trillions of tokens over months of continuous compute,
It adds up.
it adds up massively. Deep logic begins to emerge from the math. It learns grammar because understanding grammar minimizes prediction error.
Right.
It learns facts to predict the end of a historical paragraph. It learns reasoning to predict the output of a mathematical proof.
And it does all of this entirely through self-supervised learning, which, honestly, that's the actual breakthrough here.
It is. The data labels itself.
Right. Because in traditional machine learning, you need a human engineer to label a data set, like tagging an image with the word cat.
And you just can't hire enough humans to manually label the entire internet.
Exactly. But with next token prediction, the label is just the actual next word in the document you already scraped.
Yeah, by hiding the next word, asking the model to guess, and then revealing the answer that's already there in the data, that whole manual labeling bottleneck is eradicated.
It's brilliant.
The self-labeling nature of the data is what makes massive scale possible. So instead of an engineer writing thousands of explicit if-else statements for every edge case,
Which we establish is impossible.
right, the unimaginably large scale of the self-supervised data does the heavy lifting. It forces the model to infer those underlying rules dynamically.
Okay, so if the model is processing trillions of words and inferring these rules, we have to talk about what is physically happening to the architecture.
Yeah, the actual mechanics of it.
Like what sits on the disk when this process is running? Because our sources emphasize that the resulting model is not a database.
No, not at all.
It's not building a highly indexed search engine mapping keywords to documents.
Right. A traditional retrieval system, or search engine, stores information explicitly. Pre-training does the exact opposite.
So what is it doing?
It implicitly compresses human knowledge into the model's parameters, or weights. And those weights are the billions of mathematical connections we just mentioned, the ones adjusting themselves during backpropagation.
Okay, let's use a computer science analogy here. We're basically talking about lossy compression.
Yes, exactly.
Like a massive ZIP file, right?
Yeah.
But instead of compressing the literal bytes of Wikipedia articles to be unzipped later, it's compressing the actual abstract rules of the universe, as described by Wikipedia, into a mathematical matrix.
That analogy hits the nail on the head, because if it were lossless compression, the model would be exabytes in size.
Right, it would be impossible to run.
Yeah, and you could perfectly reconstruct every article it ever read. But by utilizing highly sophisticated, lossy compression of patterns, it discards the exact verbatim text to save space.
Leaving only the deeper underlying structural patterns?
Precisely.
Which, honestly, that explains why these models hallucinate or misquote things.
Yep.
Because they don't have the original text file to reference. They only have the compressed mathematical pattern of what that text generally looked like.
It's a feature of the compression, yeah.
Yeah.
And it also explained why the model can generate entirely novel code it has never seen before.
Oh, because it learned the logic, not the exact script.
Exactly. When it processes, say, 10,000 examples of a bubble sort algorithm in various languages during training, it doesn't store 10,000 text files.
Right.
The backpropagation updates its weights to represent the foundational logic of sorting algorithms.
It abstracts the logic away from the syntax. And the abstraction is stored in the weights, which keeps the system computationally viable while giving it the ability to apply that internalized logic to a brand new problem.
Which brings us to a massive logistical problem for the engineers actually building these systems.
The cost.
The cost and the planning.
Yeah.
Because if the intelligence of the model lives in these compressed weights, how do you mathematically determine how many weights you need?
Right, because spinning up clusters of tens of thousands of GPUs costs hundreds of millions of dollars.
You can't just guess.
No, you can't just guess the architecture size, train it for 3 months, and hope it compresses the patterns effectively. There has to be a structural blueprint.
And there is. The industry relies on the physics of AI training, governed by what are known as scaling laws.
Scaling laws, okay.
These laws define a strict, mathematically predictable relationship between 3 core variables:
Which are?
the amount of compute available, the size of the training data set, and the size of the model itself, meaning the total number of parameters or weights.
Translating this to standard algorithm design, scaling laws sound a lot like Big O notation.
That's a great way to think about it.
Right, because Big O tells an engineer how their algorithm's performance will degrade as the input size approaches infinity.
Yeah.
So scaling laws tell AI researchers how their model's intelligence will predictably improve as their hardware and data resources scale up.
The comparison to asymptotic bounds is incredibly accurate. I mean, scaling laws map the precise trajectory of a model's capabilities before a single GPU is even turned on.
That's wild.
It really is. It transforms AI development from this dark art of trial and error into a highly calculated optimization problem.
Because if you have a finite compute budget, like a strict ceiling on your GPU hours, you have to make an architectural decision.
Exactly. You have a choice to make.
Do you throw that compute at passing more data through a smaller model? Or do you build a massive model with hundreds of billions of parameters but pass less data through it?
And the scaling laws solve that exact optimization problem by revealing a strict mathematical ratio.
So it tells you exactly what to do.
Yes. If you increase the parameter count of your model by a certain factor, you must increase your training data by a corresponding factor to yield the optimal return on your compute investment.
Okay, so if you build a massive model but don't feed it enough data, it's undertrained.
Right.
The weights never get enough error signals to properly compress the logic.
Yeah, it's wasted potential.
Conversely, if you feed a massive data set into a tiny model, it simply doesn't have the capacity, like the sheer number of parameters, to retain all those complex patterns.
Exactly. It forces labs to allocate their resources optimally. And this predictability is really the sole reason behind the billion-dollar investments flowing into data centers right now.
It's not just blind faith.
No, the financial sector isn't funding abstract magic here. They're funding a rigorously tested, predictable mathematical curve.
Okay, so let's look at the result of that optimization curve. We secure our massive compute budget. We pass trillions of tokens through our self-supervised loop.
Yep, the run is going.
The model compresses the deep patterns of human logic into its weights, perfectly aligned with our scaling laws. The run finishes.
Finally.
Right. We have this mathematically perfect pattern matcher sitting on a server. If we expose this directly to a user through a chat interface right now, what actually happens?
Oh, it would be a catastrophic user experience.
Really?
Yeah, exposing that model directly to production would be entirely unusable for standard consumer.
Why? Because the pre-training only gives the model capability, but it doesn't give it behavior.
Exactly. Think about the objective function running on those GPUs for months.
Predict the next word.
Right, predict the next word based purely on the statistical patterns of the raw internet.
Okay, I see.
So the output of that immense compute run is what's called a raw model or a base model. It has internalized the logic, the coding skills, the facts, but it completely lacks any concept of how it is supposed to interact with a human.
Because the internet is a chaotic mix of Wikipedia articles, toxic forum arguments, and highly technical documentation.
Exactly. So if you send a prompt to a raw model saying, write a Python script to parse this JSON file,
It might not write the script.
it might not. Based on its pre-training, it might statistically predict that your prompt looks like the title of a GitHub issue.
Oh, no.
Yeah. So instead of giving you code, it generates a long thread of angry comments arguing about which JSON library is faster, and then eventually closes the issue as won't fix.
That is hilarious, but also terrifying for a product manager.
Right.
Yeah.
It is simply completing the pattern it observed most frequently. It possesses the capability to write the code,
Yeah.
but its behavior is entirely unconstrained.
It's the equivalent of a super genius back-end system that has absolutely no API, no user interface, and zero safety rails.
Yeah.
The capability is completely useless without a behavioral wrapper.
Which necessitates an entirely separate secondary engineering phase called fine-tuning and alignment. Engineers have to take that raw engine and meticulously teach it, hey, out of all the millions of personas you compressed from the internet, you must exclusively behave like a helpful, concise, and polite assistant.
I like to think of it like the pre-training builds the massive V8 engine, but the fine-tuning builds the steering wheel, the dashboard, and the brakes.
That's a perfect analogy.
You can't hand a user a standalone engine block and expect them to drive to the grocery store.
Exactly. The intelligence is baked in during pre-training, but the usability and safety are entirely distinct engineering challenges layered on top.
Okay, we've been talking about this engine as if the fuel powering it is pure. But as software engineers, we know the reality of the internet.
Oh, yeah.
It's a data swamp. We are dealing with broken HTML, tracking pixels, automated bot spam, outright garbage.
So much garbage.
How are we not just building an engine that perfectly replicates the worst, most broken parts of the web?
You've isolated what is arguably the most brutal, unglamorous, and critical engineering challenge in the entire AI stack.
The data pipeline.
The data pipeline. Everyone loves to focus on the neural network architectures and the scaling laws, but a multi-million-dollar model is strictly, uncompromisingly, only as good as the data it consumes.
And to clean that volume of data, you can't just run a Python script with some rejects on a cron job.
No, absolutely not.
Rejects breaks down completely when you're trying to parse the semantic difference between actual human reasoning and, say, a bot-generated SEO article.
You must be dealing with distributed, map-reduced jobs running across thousands of nodes just to prepare the text.
Wow.
The scale of the data pipeline is staggering, and one of the most mathematically intensive parts of that pipeline is deduplication.
Deduplication, why is that so hard?
Well, if you scrape the entire internet, you're going to encounter the exact same boilerplate text millions of times.
Oh, like the standard MIT open source license.
Yes. Or automated cookie consent banners.
Right. We value your privacy.
Exactly. And if you don't aggressively filter those out, the self-supervised learning loop is going to see that MIT license 10 million times.
And backpropagation will update the weights based on that.
Yep. The backpropagation will overweight those specific mathematical connections, and the model will implicitly learn that the MIT license is the most fundamental, important concept in the human universe.
That's amazing. So to prevent that, what do?
Data engineers use advanced probabilistic techniques like minhash to find and eliminate near-duplicate documents across trillions of words.
Because if the data pipeline fails, the self-supervised learning process will confidently and permanently learn the flaws of the data set.
Absolutely.
The golden rule of software engineering, garbage in, garbage out, doesn't just vanish because we're using neural networks.
No, it actually gets amplified.
Right. Because if your distributed data pipeline accidentally lets through millions of examples of poorly optimized, insecure code from, like, abandoned repositories.
Your raw model will compress that insecure code into its foundational logic.
And when a user asks your aligned model to generate a script, it will confidently generate insecure code because its mathematical baseline for standard code was corrupted by the data pipeline.
Exactly. A massive portion of the engineering effort at top AI labs never touches the actual machine learning algorithms.
It's all data work.
It is entirely focused on managing massive data lakes, writing complex heuristics, and orchestrating distributed compute just to get the raw digital exhaust of humanity clean enough to be useful.
It is a profoundly humbling reality. I mean, the most advanced, seemingly magical technology of our generation relies entirely on data engineers doing the tedious, brutal work of sanitizing text files.
It really does.
So let's pull all of these threads together for you, the engineer listening. We started with a chaotic, unstructured data swamp, the raw internet. We unpacked the core loop, using self-supervised next token prediction to generate mathematical error signals that update billions of weights via backpropagation.
And that process mathematically compresses human knowledge into a lossy, abstract representation of logic.
Right. And we explored how the sheer scale of that compression is dictated by strict scaling laws, turning model architecture into a massive calculated optimization problem, balancing compute, data, volume, and parameter count.
Yeah.
We saw that even after perfectly executing that optimization, the output is just a raw model.
A massively capable but unaligned backend.
Exactly, which requires fine-tuning a steering wheel to become a usable product. But the crucial takeaway here, stripping away all the sci-fi headlines, is that the foundations of modern AI are deeply rooted in the exact same software engineering challenges you face every single day.
Distributed systems orchestration, rigorous resource allocation, and the relentless, unglamorous reality of data pipeline management.
The fundamentals of robust systems engineering do not disappear when you introduce artificial intelligence.
No, if anything, the scale of AI makes those fundamentals more critical than ever.
Absolutely. But before we sign off, there is one final, pretty provocative reality we need to confront based on the mechanics we've discussed today. We established that these models gain their intelligence by compressing the deep patterns of human thought found on the internet, right?
Right.
It relies entirely on the training data being a pure reflection of human logic. But what happens to those predictable scaling laws and those carefully compressed weights when the data swamp it trains on inevitably becomes saturated with synthetic text generated by the raw models themselves?
Oh man, model collapse.
When the code base is no longer written by developers, but by the compiler itself, feeding its own lossy compression back into its next training run. Think about the asymptotic bounds of that loop the next time you push code. Catch you on the next deep dive.